just want to move this here so we can access the top of my screen. Okay, so I have logged into Dardel and to Alvis, and I will run some exercise examples here. So I'm going to talk about GPUs with Python, and this is kind of a continuation of the batch material that I talked about yesterday and the day before. This time focused on GPUs. So what is GPUs, GPU acceleration? How do I enable GPUs in Python code? And more importantly, how do I deploy GPUs at these different centers? Because that is actually one of the things that is most different between the HPC centers in Sweden. They all have different GPUs. They all access them in different ways. So this is what we will look at. So first, I will go through GPUs briefly, and then I will talk about more specifically the GPU nodes at the various centers. And how do we make a batch script that asks for GPU nodes? Because the thing is that at most centers, there are no login nodes with GPUs. And of course, even if there were, you were not allowed to run heavy jobs on the login nodes. But in general, the login nodes doesn't have GPUs. So let's look at GPUs, and also here is a CPU just to compare with. This is an example of a CPU node. It's an AMD Zen 4 node. And I will see if I can make it slightly bigger. Okay, but in any case, these CPUs, they will often be divided like this. So you have some number of cores, and this one has 256 from 0 to 255. And they are, in this case, divided up into NOMA nodes. That is, half of them share the bus and memory, and the other half share also some memory here. They can access each other's memory. It's just that it's slightly faster if you keep it inside of a NUMA node. And communication is also slightly faster within a NUMA node. They have cache memory, L1, L2, L3. The L3 is the biggest, also the slowest. And in this case, for this type of node, it is shared between 8 cores. Each of these cores have L1 and L2 cache. And of course, if you run something and you can keep it within that memory, it's very fast. And aside from having memory for these cores, you also have some disk that is connected to the whole CPU. And then out of that is connected to other nodes further out, and also the shared storage. So this is a CPU example. So you can see there is a fair number of cores, but it's nothing compared to a GPU. This is a GPU card of the type Ada Lovelace, and that is the ones that are in the L40Ss. And it looks like this. You can see that there are many, many, many more cores here. Because in this example here, each of these green dots is a CUDA core that is running single precision. And you see a number of yellow ones. Those are ray tracing cores, RT cores, and the blue ones are the tensor cores. It's zoomed in here. So this is one of these graphic processing clusters that a GPU has. And you can see how it looks more closer here. So again, tensor cores, ray tracing cores, and CUDA cores, tensor cores, and ray tracing cores. And they are connected within these blocks, and they are also connected to each other with an L2 cache. But the very obvious difference to CPUs are how many more cores there are. But also they are small cores, they are not doing a lot each. So each one of them cannot do a lot. But if you have something that's very, very parallel, and you can run on many of them, which is what you do with GPUs, then it will be very fast. So if you have a typical machine, then the GPUs will sit attached to a single node. So you have some hybrid architecture where the GPU is on a CPU. And you can, of course, run on both the CPUs and the GPUs in this hybrid architecture. And this example here is at Kebnekaise. This is Zen 4 node, as we saw above, with L4S GPUs on. And it has two L40Ss. So this is a CPU, and this is another CPU. And there are GPU cards are attached like this, one to each of them in this case. The setup can differ a little bit, but this is a typical setup. And it's clear that if you have allocated to run on the GPU card, you cannot let someone else use the CPU because that would kill the bandwidth. But if you yourself have this allocated, you can of course use both the GPU and the CPU if you have a code that is hybrid. And almost always there will be some part of it that runs on the CPU and some part that runs on the GPU. These connections here between the CPU and GPU, that is usually a PCIe interconnect, at least it is on these nodes, and that means that the data transfer is fairly slow. And that also is you don't offload data all the time to the GPU. You usually do it in the beginning of your computations. So if you look at CPUs and GPUs, then two things to think of is latency and throughput. Latency is the time spent in a sole computation, whereas throughput is the number of computations that can be performed in parallel. And if you do that, then you say CPUs has a low latency because they can do very fast computations, but they have low throughput because they can only do a few computations simultaneously. It is basically opposite with GPUs because there we have high latency, but we have also high throughput. So you can look at it as if you had a road. So maybe you have a CPU road and it looks like you have a number of cars. They are not very many, but they all go very fast. So that is the equivalent of the processors that are not so many, but all very fast. On the other hand, a GPU, could look at that as a wide road with many, many, many cars on it, but none of them go very fast. So this is a way of illustrating it. Knowing this about how GPUs and CPUs work, we also realize that not every Python program will be suitable for GPU acceleration. GPU will process simple functions very fast, And that means also that they are best suited for repetitive and highly parallel computing tasks. They were originally designed to render high-resolution images and video concurrently and fast, but they can also be used to any other parallel operations on multiple sets of data, so they are used for many different tasks that are non-graphical as well. They are very popular in machine learning and scientific computation, and any other form of processing where you can take advantage of massive parallelism. So many of the Python packages that you are using are not made, they are not CUDA aware, they cannot take advantage of the GPUs, but many of them have been written with GPUs in mind. You know, the regular NumPy package and SciPy, you could optimize the code for GPU computing if you wrote CUDA, if you used CuPy, which mimics the NumPy functions, or you can use Numba. Numba is maybe the more well-known of them, and that uses CUDA, and you can write CUDA in Python yourself, which maybe is not what you want because it's a little bit cumbersome, but you can use custom algorithms. But there is one thing, and that is that at least the newer CUDA is only for NVIDIA GPUs. If you have AMD GPUs like you do on Dardel, you would have to use HIP instead. And there are also some packages that are written for HIP. One of the most common uses of GPUs, as I said, is for machine learning and deep learning. And there you would often use something like TensorFlow or PyTorch, because that does both the CPU and GPU processing internally, and you don't need to write CUDA code. It also means that they will not run on. I don't think there's any of those that runs on AMD GPUs. But anyway, talking about this leads me into let's look at which GPUs are on the various systems and how you allocate them. And I have written down here how it's done for these 6 systems here. In the future, there will be Arrhenius, which will take over for the NSC, PDC, and C3SC, Tetralit, and Dardel and Alvis, which will, at least for some of them, become local systems like these 3 already are. But for now, let's talk about them. And I'm going to start in this order here with the ones that are used for NAISS. Alvis is meant for GPU jobs, and I think you know this. You are not allowed to run CPU jobs on it. You are not usually allowed to run non-machine learning jobs on it even. There is no node sharing on the multi-node jobs. That means exclusive is automatic. But requesting a full node doesn't mean a full node when you do it like this. This is just because this is how you get to the GPUs on Alvis. And if you want to run on Alvis's T4 A100 or the V100 ones, then you would first say, I'm using the Alvis partition. And then you put whole nodes here. And then you say hashtag sbatch minus GPUs per node equals, and then type, which is one of those 3. And then how many of them? How many is dependent also on how many GPU cards are on each type of node. So if you, for instance, were asking for a T4, then you could ask for up to 8 cards because there are 8 cards on the nodes. Whereas if you, for instance, were using the A100s, you could not ask for more than 4 cards at most. So this is what you put here. At PDC, PDC has AMD GPUs. It also now has some NVIDIA GPUs, but we don't have access to them with this course project. So to access the AMD GPUs, you put in these 3 lines. So this is the GPU partition and the nodes, and then how many tasks per node. And that gives you AMD GPUs. But now, newly, Dardel has also gotten 8 Grace Hopper nodes on the GPU Grace Hopper partition. And these each has 4 NVIDIA Grace Hopper H100 GPUs and 4 NVIDIA Grace ARM CPUs. So that is a total of 32 of these Grace Hopper superchips. And these are the types that are going to be on Arrhenius. So I guess you can apply for a project on Dardel that in this petition if you want to test them, but as you can see, there isn't very many of them. But this is what will be on Arrhenius, and it's not that far in the future that we can access Arrhenius. So this is what you would put in your batch script or interactive job in order to access them. And here you use the GPU GH partition to get to the GPU Grace Hopper partition. And a comment is that now they are different resources that you need to ask for in your compute project in order to get both types of GPUs on PDC. NSC, that is the tetralit. It has NVIDIA T4 GPUs, and you access them this way here. So is batch minus N1 minus C32 and minus GPUs per task equals 1. So that is the NAISS systems. Then we have 3 local systems, and I'm not going to talk so much about them. I'm just saying that LUNARC has A100 and A40 GPUs, NVIDIA, and this is how you ask for them. HPC2N has a whole lot of different GPUs. V100s, A40s, A6000s, L40Ss, A100, H100s, and M. These are all NVIDIA GPUs, and then there's an AMD GPU, the MI100, mostly for testing. To access these, you need to have a course project that is using the GPU partition on the GPU resource at Kebnekaise. And you access them by saying how many GPUs you want and which type. And type is here, and you can see how many you can ask for from each of them. UPPMAX, new cluster Pelle has GPUs, L40S GPUs, and H100 GPUs. And this is how you can ask for them. So it is similar to how you do on Alvis, I believe, or maybe PDC. Anyway, you ask for the partition, which should be GPUs in either case. And then you're saying what type of GPUs, L40Ss or H100s, and then how many are the GPU cards, which again could be up to 10 if it's L40Ss, and up to 2 if it's H100s. Okay. So you can go back and look at this here when you want to see how you get the GPUs on in your batch script. So I have a number example. Number is installed on some of the centers as a module. HPC, LUNARC, and C3SE. If you are on UPPMAX and NSC, you will use virtual environment. I'm not sure if this is still true for UPPMAX. Is there anyone from UPPMAX here that can answer this? It looks not. This was the case when I tested, but that is a little while ago. PDC's Dardel has AMD GPUs and number up to version 0.53.1 had compatibility with CUDA. The newer numbers that you need do not have this compatibility, and the older ones are too old to work with anything else, so you cannot run this on Dardel unless you're running in the GPU Grace Hopper partition, which our course projects doesn't have allocation on. There is no number example for PDC. There is another example that you can play with. And in order to do that, you need to install HipPython. But I also have a different example further down so that those on Dardel will have something to test run. So I will test on Alvis right now, but I will just briefly mention it here. Here are some examples on how you would simply go about if you're on Pelle, both if you're doing it as an interactive job or if you are doing it as a batch job. Like HPC2N as an interactive job and as a batch job. Lunar as a batch job. C3SE is the one that I'm going to test run here. And then there's also an NSC batch example. So I will look at this one here for C3SE for Alvis. And it runs the Python code add list pi, and you will submit it with sbatch add list.sh because I named the batch script add list.sh to remind me that it's using the add list pi. And it has many of the same features as you have seen in batch scripts before. It has the shebang that tells it to run in the bash shell. It has the project ID. Also, you're asking for a number of time, hours, minutes, seconds, here 10 minutes. In the Alvis partition, as we saw further up. And then I'm asking for T-Force GPUs, and I'm saying I want 2 GPU cards. And then I'm giving an example of how you split output and error files instead of getting it into the slurm jobid.out file. Here you are splitting it with the sbatch ---- output and the sbatch ---- error. You can name it as you want, but the advantage of naming it something that contains %GA is that each time you run it, you get a new output file with the job ID environment variable in it. And that means that they will be different for each run and they will not be overwritten. So you can put something here, but I suggest you put %GA. And then we load any GPU modules we need and any prerequisites on Alvis. It's like this. So this is what you load in order to get everything on Alvis. And then you run it with Python and the Python script. Now, I have it here in HPC Python. So I'm going into exercises. And in exercises, I'm going into day 4. And under day 4, just like for the other days, there are some directories for each of the centers. And there's one for programs. In programs, you have this add list here. You can also see it here. But it is in this directory. It's here, add list pi. And it's the same one that is shown on the website. But I will leave the programs directory and I will go into C3SE where I have the example codes for Alvis. Here I have the addlist.sh, the one I showed here. And just like in the other days, I have something I need to change. Namely, in this path here, I want to make sure that the path is correct. And it becomes correct when I change this to my name on Alvis, to what I named this directory. And I named it thus. And then it goes and points to the programs directory. So it's an environment variable that I create that points to this, so I don't need to put it in front of my program each time. And now this should be fine. So I'm saving and exiting. I'm saying yes here to save it. And then I am submitting it with sbatch add list. Let's see how it goes. It's pending, and it might be pending for a while, so because of this, I'm going to continue. And I will cover here that there is an example for Dardel, as I mentioned. And this example uses HIP, and that is because the ones we have access to are AMD. So I will use an example HIP C++ code that's called Hello World GPU CPP. So it's a C++ code, and I got it from here. And it is also here if you want to copy it, and it's also in the programs directory. And this is how you would run it. So I will just briefly cover this. Again, this is like before. We're asking for project ID, time, and the GPU. We want one GPU here. And then I am loading a module here, rockm, that is used to run this code on Dardel, and then I'm also loading this module here for Cray to set the accelerated target to this type of node of the architecture that we have here for these AMD GPUs. And then I am going to use the AMD HipCC compiler. And in order to make it easier, I am actually compiling it in this batch script. That is something you normally should not do because it compiles it each time, then it takes extra time and so on. So don't usually do this. You would usually just compile it in your terminal window before you submitted it. You can if you want to, and then just comment this out, this line here. In any case, I'm then running it with this command here. So if you're on Dardel, you can use this example here to test it with. We have then gotten to the exercises, which I will briefly cover, and then you should have about 15 minutes to test to run either this number or the HIP on the system you're at, or you can also play with this if you have more time. This is an implementation of a 2D integration problem. It's actually a continuation of the ones that Pedro also talked about. And the codes are here. And it uses number. So this is not for Dardel. And you can try and create a batch script to run those two versions. And the programs themselves will be located in the programs directory. So either go to that directory and create your batch script, or put in this environment variable that points to the program. So you can use the example from one of the others. So take the batch script from a center that you are working at, and then try to modify it to get these two to run. And if you need it, then the solutions can be found here as well, and they are also in the directory for each of the centers. So we have looked at deploying GPU nodes with Slurm, and it can be done interactively as batch scripts. And the number package is often used, except if you have AMD GPUs, which means you probably use HIP instead. And you can also, of course, run from inside desktop on demand. And I haven't covered this here, but that could also be the case. And there you can also ask for GPUs. And yeah, I mean, that is done the same way as we saw yesterday, where you simply ask for GPUs instead of CPUs. And there are some links here. I also put in the link to this page here about the new Arrhenius system. It's just located here on this website here that Björn has put this together so that you can see which architecture will be there. But go ahead and try and do this example here. Try and run it on your system, or run this if you don't have NVIDIA's GPUs. And when you've done that, if you have time, you can try and do this exercise, but at least try and do this here. So let's take exercises until it's 12 o'clock. And I'll say that when it's 12 o'clock, then you can take lunch, and then we can take a short time for questions, maybe after the lunch. So do exercises to 12 and then take lunch until 1 o'clock. And yeah, see you back at 1 o'clock.